The exceptions to using column C for ranges are specifically for those ranges rated over 15 kilowatts, plus an additional 1 kilowatt for each additional 25.4 centimeters or 10 inches of cooking surface width exceeding 91.44 centimeters or 36 inches. The reason for these exceptions is that ranges with higher power ratings demand larger conductors to safely carry the increased current. When dealing with electrical installations, it is crucial to select the appropriate conductor size to prevent overheating, voltage drop, and potential fire hazards. The National Electrical Code, or NEC, provides guidelines and tables to assist in this selection process. For household cooking appliances, the NEC outlines specific requirements based on their power ratings. For instance, Note 3 is intentionally less specific because its scope encompasses all household cooking appliances rated more than 1.75 kilowatts but not exceeding 8.75 kilowatts, irrespective of their specific type. This broad category includes not only ranges but also ovens, cooktops, and any other similar appliances used in a residential setting for cooking purposes. The NEC aims to ensure safety and standardization in electrical installations by providing these detailed instructions. Understanding these regulations is essential for electricians, contractors, and anyone involved in electrical work to ensure compliance and prevent potential hazards. Conductor sizing is a critical aspect of electrical design and installation. It involves selecting the appropriate size of electrical conductors to safely carry the intended current. The NEC provides tables and guidelines to assist in this process, taking into account factors such as the ampacity of the conductor, the ambient temperature, and the number of conductors in a raceway or cable. Firstly, determining the load is necessary. This involves calculating the total current that the circuit will be expected to carry. For a range, this would be based on its nameplate rating in kilowatts, converting that to volt amps, and then dividing by the voltage to find the current in amps. Secondly, selecting the appropriate conductor size requires understanding the ampacity ratings of different conductor types and sizes. The NEC provides tables that list the ampacity of conductors based on their insulation type and temperature rating. Thirdly, considering dirtying factors is crucial. These factors account for conditions that can reduce the ampacity of a conductor, such as high ambient temperatures or the presence of multiple conductors in a raceway. Dirtying factors are applied to the conductor's ampacity rating to determine its adjusted ampacity. The adjusted ampacity must be equal to or greater than the calculated load current. Let's consider the specifics of range calculations. When calculating the conductor size for an electric range, the NEC provides specific rules and guidelines. These rules take into account the intermittent nature of range usage and allow for demand factors to be applied. Demand factors reduce the calculated load current based on the assumption that not all heating elements of the range will be operating at their maximum power simultaneously. Firstly, calculating the base demand load is necessary. For ranges rated between 8.75 kilowatts and 12 kilowatts, a demand factor of 8 kilowatts is typically applied. This means that the calculated load current can be based on 8 kilowatts rather than the full nameplate rating of the range. Secondly, adjusting for higher rated ranges is needed if the range is rated higher than 12 kilowatts. The NEC provides a table that allows for adjustments to the base demand load based on the range's rating. For example, for ranges rated between 12 kilowatts and 27 kilowatts, the demand load can be increased by 5% for each kilowatt above 12 kilowatts. Thirdly, applying the demand factor to calculate the conductor size is important. Once the demand load has been calculated, the appropriate conductor size can be selected based on its ampacity rating. The conductor must be sized to carry the demand load current, taking into account any applicable dirtying factors. Consider an example. Let's say we have an electric range rated at 15 kilowatts connected to a 240 volt circuit. To calculate the conductor size, we would first determine the base demand load, which is 8 kilowatts. Since the range is rated higher than 12 kilowatts, we need to adjust the demand load. The range is 3 kilowatts above 12 kilowatts, so we increase the demand load by 5% for each kilowatt, resulting in a 15% increase. 15% of 8 kilowatts is 1.2 kilowatts, so we add this to the base demand load, giving us a total demand load of 9.2 kilowatts. To find the current, we divide 9.2 kilowatts, or 9,200 volt amps, by 240 volts, which gives us a current of 38.33 amps. We would then select a conductor size that is rated to carry at least 38.33 amps, taking into account any applicable directing factors. In the context of the original question, the NEC provides specific rules for ranges rated over 15 kilowatts. These rules are designed to ensure that the conductors are sized appropriately for the higher current draw of these larger ranges. Firstly, ranges over 15 kilowatts may require larger conductors than those calculated using the standard demand factors. The NEC allows for an additional 1 kilowatt to be added to the maximum demand for each additional 25.4 centimeters or 10 inches of cooking surface width over 91.44 centimeters or 36 inches. Secondly, this additional demand load is intended to account for the increased power consumption of larger cooking surfaces. Ranges with wider cooking surfaces are likely to have more heating elements operating simultaneously, which increases the overall current draw. Thirdly, the NEC requires that the conductors be sized to carry this additional current. This ensures that the conductors are not overloaded and that the range can operate safely and efficiently. In addition to the specific rules for ranges, the NEC also provides general guidelines for conductor sizing that apply to all types of electrical circuits. These guidelines cover factors such as the ampacity of conductors, the ambient temperature, and the number of conductors in a raceway or cable. Firstly, the ampacity of a conductor is its current carrying capacity. This is the maximum amount of current the conductor can safely carry without overheating. The ampacity of a conductor depends on its size, material, and insulation type. Secondly, the ambient temperature can affect the ampacity of a conductor. Higher ambient temperatures reduce the ampacity of a conductor, as the conductor is less able to dissipate heat. The NEC provides directing factors that must be applied to the ampacity of a conductor when it is installed in a high ambient temperature environment. Thirdly, the number of conductors in a raceway or cable can also affect the ampacity of a conductor. When multiple conductors are installed in close proximity, they can generate heat that reduces their ampacity. The NEC provides directing factors that must be applied to the ampacity of conductors when they are installed in a raceway or cable with multiple conductors. In summary, understanding the NEC guidelines for conductor sizing is essential for ensuring the safety and reliability of electrical installations. When sizing conductors for ranges, it is important to follow the specific rules for ranges rated over 15 kilowatts and to take into account the demand factors that apply to range loads. Additionally, it is important to consider the general guidelines for conductor sizing, including the ampacity of conductors, the ambient temperature, and the number of conductors in a raceway or cable. Considering an 8.75 kilowatt range versus a 1.75 kilowatt appliance, the distinction lies in the power demand and how the NEC addresses the wiring requirements. Firstly, a range typically encompasses multiple heating elements and a larger overall power draw, requiring a more robust electrical circuit. The NEC recognizes this by providing specific demand factors and guidelines tailored to range installations, allowing for a reduction in the calculated load due to the intermittent nature of cooking. Secondly, a 1.75 kilowatt appliance, on the other hand, represents a smaller, more consistent load. Its wiring requirements are generally straightforward, based on its continuous current draw. The NEC applies standard ampacity rules for branch circuits, ensuring the wiring is adequately sized to handle the load without significant demand factor considerations. Thirdly, the NEC approach differentiates between these appliances to ensure both safety and efficiency. Ranges necessitate special attention due to their potential for high instantaneous power consumption, while smaller appliances can be accommodated by general wiring practices. Note 3 is not specific because it applies to all household cooking appliances rated more than 1.75 kilowatts but not more than 8.75 kilowatts, regardless of type. This includes ranges, ovens, cooktops, and other appliances. Understanding the specific requirements for each type of appliance is crucial for ensuring safe and compliant electrical installations. This is also because different appliances may have different duty cycles and operating characteristics. A range, for example, may have multiple heating elements that are used intermittently, while a cooktop may have a more consistent power draw. The NEC takes these factors into account when providing guidelines for conductor sizing.